Reinforcement learning requires rewards to determine if the robot has made progress towards the goal. However, the rewards are often defined in ground truth state space, which is not directly available, especially when manipulating deformable objects, such as preparing food or folding laundry. Many previous approaches try to get around this problem. One approach is to add extra sensors to measure the states, such as using motion capture markers to track the pose of the object, or attaching IMU sensors to the door. However, sensors can be costly and are not always applicable. Another approach is to first train in simulation, where states are available, and then transfer to the real world. But sim-to-real transfer has proven difficult, and building simulators also takes additional effort. As such, many recent works aim to learn a reward function. They do so by first learning a feature embedding phi from the observation, and then compute the rewards based on the distance in the feature space. However, learning the reward function can be difficult, as we will later show. Next, we will investigate how to find a proxy reward function that is based on observation without knowing the ground truth state. In goal conditioned reinforcement learning, sparse rewards are often used to denote the achievement of the goal. A positive reward is given when the current state is sufficiently close to the goal state. Here, the green circle shows the region that receives a ground truth positive reward when SG is the goal. On the right is the observation space, where we want to specify a proxy reward function that matches the ground truth rewards without knowing the ground truth state, and the blue circle represents the region that receives a positive reward based on the proxy reward function. Now there will be two types of reward misclassifications. Given a state ST1 that receives a positive reward, if the corresponding observation OT1 is outside of the blue circle, it will receive a negative reward, and thus creating a false negative. Similarly, for a state ST2 that is outside the green circle, the corresponding observation OT2 might be inside the blue circle, and thus become a false positive. Now, which type of mistake is worse? It turns out that false positive rewards are more harmful than false negative rewards, as the robot is rewarded for not reaching the goal. As a simple example, we first randomly flip the rewards to increase the false negative rewards and see the learning curves. We can see that the learning is pretty stable as the number of false negative rewards increase. On the other hand, if we start to increase the number of false positive rewards, the performance downgrades very fast. Given that we know false positive rewards are very bad, what reward function should we use? We propose to use an indicator reward function, which only gives a positive reward when the current observation exactly matches the goal observation. This eliminates all the false positive rewards, and learning with indicator reward is possible when combined with goal reliability. Indicator reward function gives very sparse positive rewards. To further accelerate learning, we introduce reward balancing and reward filtering. Reward balancing balances the positive and negative rewards by changing the goal relabeling strategy, and reward filtering reduces the false negative rewards by filtering out uncertain rewards. Learning with the indicator reward function is not optimal due to the false negative rewards, but the suboptimality can be bounded. For example, assuming we're at ST and the goal is SG with a green goal region here. Given the ground truth reward function, the agent will go to the closest state in the goal region, which is S here. But with an indicator reward, the agent will take a longer trajectory in order to go exactly to the goal location. But this trajectory will always be shorter than going first from ST to S and then from S to SG, thus giving us the bound. Now we will show our experimental results that compare using an indicator reward function to those that learn a reward function. The first task is to push a rope to a goal configuration. The first method uses VAE representation to give rewards, which focuses on salient feature of the observation and does not perform well. The second method uses a distributional planning network to learn a representation, but also struggles to learn here. Finally, we show our method, which can successfully push the rope to the goal configuration, and it does not learn a reward function. Here, we show quantitative results on more environments with RGBD images as observation. Our method consistently outperforms the baselines and is comparable to the Oracle, which uses the state-based ground truth rewards. Finally, we show that our method works well on a real-world reaching task on a Sawyer robot with visual input. It can reach to an accuracy of 5 centimeters.